because last time we spent all this time talking about, like, orbitals and gross things like that you guys aren't as interested in, and I get they're more theoretical, but those will be important when we talk about electrocyclic reactions, maybe today, maybe on Wednesday. We'll see how far we get. But let's go ahead and do some OChem here. So if I want to do some reactions with dienes, perhaps you'll remember something like this. This reaction here, standard addition to an alkene, electrophilic addition, you end up, how many carbons do I have here? 4? 5 carbons. You'll end up putting your bromine on the more substituted position. You'll have your Markovnikov type of idea. You're going to end up forming your carbocation. I think I do have too many carbons. There we go. And so you'll end up, making your tertiary carbocation and sticking your bromine on afterwards. 2 steps, right? We're going to see with dienes, things are a little bit different. If we just take a standard diene and throw our HBr at it, we're going to end up getting actually a mix of products. So you're going to see that you're going to get this guy here and this guy here. You're going to end up with 2 different products, assuming you've just got one equivalent of HBr in there. And we're going to kind of look at why those are going to happen. We're going to see that there's kind of 2 processes here, which this one is going to be called the 1,2 adduct. It's added to the 1 and 2 positions of that molecule. And this is just relative to each other. So we're saying we've added a hydrogen here. I know we don't typically draw our hydrogens, but remember HBr has a hydrogen on there. So we're adding a hydrogen onto one position there, and then we're adding it on, we're adding the bromine next to it, 1 carbon away. We're going to see with the second product, it will be called the 1,4 adduct, because we're going to be adding our hydrogen to what we could call carbon 1, and then we're going to add the bromine on, relatively speaking, the 4th carbon. So 3 carbons away from there. And so if we want to look at this, we can see how these products will form. We can say, aha, well, we know this is a carbocation process. So if we want to take a look here, if we are saying we're going to put some HBr in this thing, let's go ahead and do a mechanism here. So remember, in this process, your alkene will attack your electrophile. And so we're going to end up putting a hydrogen on our alkene. And I'm going to draw that hydrogen in, I'm going to draw it in green, because why not? We'll keep it special. So that hydrogen that we just added on from the HBr will leave us with a carbocation at this position, right? So this was, carbon 1, carbon 2. So we've got our carbon 1 has attacked the hydrogen, and now we have an allylic secondary carbocation here. Remember, with this, you're never going to form the opposite product. You're not going to form this thing. You are definitely never going to form that, because now we have a carbocation that's primary, which is, first off, a no-no. Secondly, we now have a carbocation that can't even resonate. So big no-nos here. Don't ever form that guy. Remember that in this process, you will form the more stable carbocation. So this is from chapter 7, so you may want to refer back to that addition to alkenes, just to remember this kind of process. But suffice it to say, you get this kind of intermediate here. And if you go ahead and stick on your bromine right away, you're going to end up with that 1,2 adduct that we saw before. You're going to have the hydrogen on what could be carbon 1, and then the bromine 1 spot away from that. Or, because this is allylic, we can resonate it as well. Remember that carbocations will do all sorts of crazy stuff in your molecules, and in one case you can resonate it. If we resonate it, we can just move that double bond there. We end up with, and I'm going to draw my H in again. We end up now with our carbocation over here. And, again, we see a primary carbocation, but this is primary allylic, so it's not as bad as a plain old primary carbon. That being said, though, between these two molecules, I'll go ahead and label them, both of them, which one of those is going to be kind of a more stable intermediate? The top molecule there with the carbocation on carbon 2 or the one on carbon 4? Which one's more stable as an intermediate? Which one do we think? Also, where is everybody? We're missing like 10 people. Today I have to submit my attendance roster, so I don't want to do attendance. But we'll do it. Alright, someone, tell me, which one of these is more stable?
I think carbon 4.
Carbon 4 is more stable? Why?
Just because you said it was primary.
Alright. So, is primary a good thing for carbocations? Or a bad thing? If we look at a non-allylic case, remember, you can have a primary carbon here, a secondary carbon here, tertiary carbon here. Remember, the best place to put a carbocation is on your tertiary one because of hyperconjugation. Orbitals, CH bonds, the orbitals from the hydrogens can stabilize carbocations, so you want to put carbocations generally on the more substituted carbon. So at least if you just have no double bonds, tertiary is best, followed by secondary, followed by primary, because you have hyperconjugation stabilizing the more substituted ones. So with that in mind here, which of these, so allylic ones still follow the same rules. We're going to see allylic ones are more stable in general than any of those might be, but we're still going to see that tertiary is the best, followed by secondary, followed by primary. So indeed we're going to see that the top molecule is the more stable intermediate. So it's the opposite with carbanions, though. There you want primary. Primary for carbanions is more stable. Alright, so if we go ahead and kind of complete the mechanism here, if we're going to be adding on the bromine, it's just going to, stick itself onto the carbocation, because it's negatively charged. I'm going to delete that for now. We can do the same thing with the second one. And if we do this, we will end up with our lovely molecules. And so you can see here how we've come up with these two products. So we'll form our carbocation just like we would before, as in a plain old electrophilic addition to an alkene. We're going to potentially resonate it, but we see that already we kind of have the more stable intermediate already. We don't need to resonate it. But let's talk about the products. Perhaps we remember something about alkenes and their stability. What do we remember about that? What kind of alkenes are more stable in a product? If you have the choice between forming multiple alkenes, what's going to be the best option? not necessarily with these two molecules. You can give an answer with these two molecules, or you can just say in general, what kind of type of alkene is going to be more stable?
The more substituted it is?
More substituted, exactly. So you want your kind of alkene to be more internalized. You want it to be more substituted. And so looking at these two products, which one of them is the more substituted product? For the alkene, at least. Which alkene has more carbons on it?
The 1,4, because it's the alkene would be, yeah.
Yes, absolutely, I agree. So the 1,4, the alkene you get there has 2 carbons on it. The 1,2 has 1 carbon on it. So we're going to see that this guy, the 1,4, is going to be the more stable product. Right here, because the it's the more substituted alkene. So we see here that we have 2 products from this reaction. One of them comes from the more stable intermediate, and the other one comes from the one results in the more stable product. So the one that comes from the stable intermediate is going to be formed faster, right? Because we know that the more stable your intermediate is, the more likely it's going to hang out kind of in that kind of resonance contributor. So the more stable your... No. Shut up, Alexa. The more stable your intermediate is, the longer it stays in that state. And so the more likely you are to be attacked by your bromine here and form your 1,2 adduct. By contrast, though, we're going to see that the less stable intermediate will end up giving us the more stable product. And so if we want to look at these in terms of a graph, our absolute favorite things in chemistry, if we've got our butadiene here, we kind of have 2 options. Maybe those are not energetically, this graph may not be to scale, but this would be our kind of 1,2 adduct here. And this would be our 1,4 adduct. So we're going to have kind of an exothermic reaction in either case. And we're going to see here that the 1,2 adduct has a lower activation energy because it has a more stable intermediate. But it results in a product that has higher, you could say, enthalpy or higher energy than the 1,4 adduct does. And so we're going to see a little bit about why this is, but suffice it to say that we're going to be able to kind of choose the distribution of products we get by messing with the temperature. So we're going to see that we have terms for these. We're going to say that this 1,2 adduct is called the kinetic product, and the 1,4 is called the thermodynamic product. I can spell, I swear. That looks right. Your kinetic product is the one that's formed from the more stable intermediate. I'm just going to write this down here. More stable intermediate is going to give you your kinetic product. So we saw that secondary allylic carbocation was more stable than the primary allylic carbocation. So the one that intermediate will lead to our kinetic product, which was the 1,2 addition. And if we take a look at the opposite side, the more stable product, in this case we're looking at the more substituted alkene, is what is called the thermodynamic product. So again, the more stable intermediate leads to the kinetic product. They're not the same because it's an intermediate, right? But the more stable product is your thermodynamic product. And for this particular reaction, if we want to say the 1,2 versus 1,4, we can look at some product distributions here. That's your 1,2 product. That's your 1,4 product, not drawing in the hydrogens this time. I have the numbers here somewhere. Let's see. Where have I hidden these? Ah! So if we're looking at, say, 0 degrees Celsius versus, say, 40, the product ratios you get here are going to be the following. 29, and then I can do this math, 85, yes. So we see here, depending on the temperature you conduct this reaction, you're going to get a different kind of array of products out. And this is what we kind of are going to be talking about when we say thermodynamic control versus kinetic control of your product distribution. So we see at lower temperature, the kinetic product is favored. But at high temperatures, the thermodynamic product is preferred. So we see that, right? We see at 0 degrees Celsius we have more of the 1,2 adduct, which came from our more stable intermediate. And we're going to see that in the other case, once we heated things up, we're going to get more of our thermodynamic product. Easy way to remember this trend, by the way. Thermodynamic has the prefix thermo in it, right? Thermo meaning, thermal, temperature, that sort of thing. That's one way to kind of remember this. At higher temperature, you have more thermal energy. You're going to get the thermodynamic product more likely to happen at higher temperatures. So that's one way to remember it. And there's a lot of ways to explain this. We can say in terms of activation energy. If we go back up to that lovely graph, remember we have activation energies here. We have an activation energy here versus another. How am I going to draw this? We have two different activation energies. So at lower temperature, we're going to have fewer molecules with high enough energy to overcome that energy barrier. So we will end up with our lower activation energy product, which is the kinetic product. We might say this has something to do with equilibrium as well. At low temperatures, we're going to, let's see if we can remember some 102 stuff here. Remember that if you have an exothermic reaction and you have higher temperatures will, sorry, this should be equilibrium. According to Le Chatelier's principle, remember high temperatures for an exothermic reaction will push things back to reactants. Perhaps. So if you end up making your reactant more, you're essentially saying, okay, if I go backwards, which one of these is easier to go backwards? Well, that's this one here, right? This product has a lower hill to get over to go backwards in a reaction. The 1,4 has a greater thing. Not only is it lower energy to end with, but it also has a higher activation energy. So it's much less likely that our 1,4 product is going to be reverting back to its starting material. And so, in terms of Le Chatelier's principle, by the reaction going back to reactants more, you're more likely to break down your kinetic product than you are to break down your thermodynamic product. And each time you go back to the kind of starting material, you're then rolling the dice to see if you end up with the 1,2 or the 1,4. And so, as a result, by going back to the reactants, even if only a small portion is the thermodynamic product, each time you send it back, you're going to end up accumulating more and more thermodynamic product over time. And so, as a result there, the more, your higher temperature is going to end up giving you more thermodynamic product overall. So, again, reversible reactions. All reactions are reversible. These are exothermic reactions. So, if you heat them up, you cause things to be more likely to revert to the reactants. If you do that, you then give those reactants another chance to kind of decide which product they're going to make. And so, after a given amount of time, you will end up statistically producing your more stable product after a while. And so, I get it. Maybe not so, fresh in your mind, because for 102 now it's been at least 2 semesters, right? And plus 102 is, you probably have forgotten all of it anyway because you didn't really use much of it in 105, and I get that. But that's another reason. Here's a third one. Do you remember this? One of our favorite equation, Gibbs free energy. You thought you were done with that as well, didn't you? Unfortunately, we're not. So we can explain this kind of distribution in terms of free energy. And we're going to see there later on why this is the case. But remember here, we're going to be dealing with temperature effects with these, and with enthalpy effects, right? And entropy. Remember, we want negative delta G overall. These reactions are exothermic, so our delta H is negative. But our delta S is also negative, unfortunately. Right? How do we know delta S is negative? We are taking two things, turning them into one thing. Whichever one thing we end up making, whichever product. So, entropically, these are not favorable reactions. Remember, these are going to be exothermic, but our delta S is also negative. So, in order for delta G to be negative, we need a lower temperature for spontaneous reactions to happen. So we're going to see here that we're also going to be dealing with temperature effects in terms of delta G. Again, things that you've probably forgotten. Isn't that fun? This will be kind of more important when we talk about Diels-Alder reactions, unfortunately. But we can kind of see this happening here too. We're going to see that these entropy and enthalpy effects still do have some factor into why we get certain products over certain other ones. So if we want the reaction to happen kind of at all, we're going to need low temperatures. But if we throw extra heat at it, we're going to end up reversing our reactions. Remember, that's part of delta G as well. As soon as you make delta G positive, you end up going reverse. Maybe. Somewhere in there. Isn't this a fun class? You have to review everything you've learned from the last 5 semesters that you've all forgotten. So remember, at high T, delta G becomes positive. Maybe. And then reaction goes reverse. I'm saying the same thing I'm saying before. So we're going to take our products, send them right back to the reactants. And once we do that, we then have the choice to go to either product, the 1,2 or the 1,4. If we take a look at the graph, remember that delta H, delta H is the difference between your product energy and your kind of starting material energy. Which of these has the bigger delta H? It's the 1,4, right? 1,4 is more exothermic. So, if the 1,4 product has a more negative delta H, that means we need more temperature to reverse it. Isn't this fun? Thermodynamics, you thought you were done? Do you remember this at all? Delta G equals delta H minus T delta S? Here, why don't we do it with like fake numbers? Let's say delta H for the 1,2 is negative 5 kilojoules. Whatever. We're going to put fake numbers. I'm going to make this hopefully easier to understand. Okay, so delta H for 1,4 is bigger as in magnitude. It's a bigger negative. So if we want delta G to be negative, let's write out our equation again. We see that if we're going to add the same T delta S for this, for our 1,2 reaction to go in reverse, we could see that T delta S just needs to be greater than 5 kilojoules. Right? For these reactions, we can say delta S is about the same, because we're both taking kind of 2 molecules, turning them into 1 molecule. So really, it's about the temperature. If we do this, to get delta G to go positive, to reverse our reaction, we need to have it equal to 10 kilojoules or more. And since delta S is equal for both of these reactions, or very similar, we can see that it's mostly this temperature thing that we need to deal with. So, as a result, this takes less temperature to reverse than the other one. And so you can either see that from the graph. We could see, okay, it's a smaller hump to overcome to go backwards. We can also say it in terms of the other one, it's a larger hump to go over to get backwards. And there's also this kind of dependency on more temperature to get it to go backwards. And so if you're going to have things going backwards, by heating it up, again, each time you start over, you'll take, your reactant and give it a choice. And so each time you go backwards, you have a new choice. And eventually you end up getting more of your stable product in the end. And I get it, it's a bit of a long-winded conversation about that. But if all you care about is not understanding why, suffice it to say, kinetic product, favored at low temperatures, comes from less reactive, your more stable intermediate. If nothing else, thermodynamic product is your more stable product, and that comes from high temperatures. Alright, so if nothing else, that's where all this stuff, that's what all this is here to explain. So, alright, so, but the trends are kind of the takeaway here. So, but just showing you again, this stuff is built on fun stuff that you've learned before, maybe. Perhaps with Gellert, way back when. So, okay. Are we done with thermodynamics? I think so. Let's take a break from thermodynamics. Let's do a couple more examples of this, and then we'll talk about Diels-Alder reactions. So, let's say we have this guy, and let's react it with HBr. That's one equivalent. With the previous one, with this kind of previous reactant, it was completely symmetrical, right? There was, there's no reason we've attacked starting at that right double bond. We could have started with the left double bond to react with the HBr, right? Doesn't really matter because it's symmetrical. Let's take a look at a non-symmetrical case. We get a couple of carbocations out of this if we were to go ahead and do the first step. Break one of the double bonds and form a carbocation. If we break that top double bond, this is kind of the first step if we break the top double bond, right? We're going to form our carbocation on the more stable center. We could also say, let's break that bottom double bond. And we're going to end up having our carbocation here instead. So, two options. Okay. We're going to see that these could give us products directly through 1,2 addition. Let me put the hydrogen on the bottom, by the way, so we know where it came from. Since our diene is now asymmetrical, we're going to end up with 4 products this time. And we're going to be able to kind of determine which one is going to be the best kinetic product, which one is the best thermodynamic product. Let's take a look at this one first, this top molecule first. So if we have reacted our top double bond. I totally meant to do that with this instead. Okay. Let's look at this one. And let me do some rearrangement. I'm going to move this guy up to the top just so it's out of our way. So these are the two kind of intermediates we could have. So if we have broken our top double bond, we end up with the left molecule there, or the middle one, I suppose. If we break our bottom double bond, we'll end up with the one on the right. Let's look at that first case. Just like before, we can resonate this. If we resonate this molecule, we can end up moving our double bond. And now we have our carbocation on the bottom. I'm going to erase that arrow just because we're going to have our bromines coming in and I want to do those. Just like before, we have two options. We can attack from either resonance form. So we can go ahead and go on there. Or we can say, okay, we're going to go on here. Giving us our 1,2 and 1,4 products, right? Did I draw that right? Yes, okay. And here's our 1,4 product. Just putting on where our carbocations happen to be. Okay. Let's just number these product 1 and product 2. And let's go ahead and look at the other place of attacking. So with this, let's take a look at this one now and see what products we end up getting out of this one. So whichever side we attack with matters this time because we're asymmetrical. Move it up a little bit. With this one too, we can resonate just like before. We're going to get a 1,2 and a 1,4 product from this same, just on this side of the molecule. If we resonate, we end up moving our double bond to the side there and put our carbocation up top, and we've got our H on the bottom. And if we go ahead and now stick our bromine on, bromide I suppose, we're going to end up with our products. So we have our 1,2 product just like before, and then we're going to have our 1,4 product. And we can label these 3 and 4. So, let's see if I can do it this way. Will this give me all 4 at once? Yes. So, looking at these then, we've got kind of 4 potential products out of this. We formed 2, we could break either double bond to make 2 different intermediates. Each intermediate can resonate, and we're going to see we end up with 4 products. With regards to these, which one of these products do we think is going to be the most stable? One, 2, 3, or 4. And if some of them are like equally stable, we can have that as an option.
2 and 4.
2 and 4, I would say, yeah. So 2 and 4 are going to be, our 2 and 4 are going to be thermodynamic products, because those give us our more substituted alkenes, right? In terms of kinetic product, though, which one of these intermediates is best? Or if there's several that are of equal goodness, which intermediate is the most stable? So which of these carbocations is the ideal one? And we'll do the same numbering system. So
this does have to be the least substituted?
not quite. And so, therefore, that might mean the most substituted, right? So just like before, carbocations, remember the best way is tertiary, right? We want tertiary carbocations, and especially if they're allylic, right? All of these are allylic carbocations. But we're going to see 3 of them are secondary, and 1 of them is tertiary. And since tertiary carbocations, again, are the best ones, which one is the tertiary carbocation?
Number 1.
Number 1 is, right. So, we're going to see that number 1 is our kinetic product. And so, we can kind of label these, right? So, if we want to think now, finally, about which of these thermodynamic products is better, well, they're about equal, right? So there's not really a huge difference there. So, poor product number 3, though, is just unfortunate. It's not really going to be formed as much of these. So if we were to kind of make a product distribution, we could say at low temperatures, we're probably going to get our kinetic product first. This is kind of going to be our product distribution. We're going to get more of product number 1, our kinetic product. We're going to have a mix of the other two. And then we're going to end up with kind of our third one. Just because it's neither kinetic nor thermodynamic, it's just kind of by itself. It comes from a secondary carbocation, and it's just going to be like kind of less likely to happen. If we're to put it at high temperature, again, we're probably going to have 2 and 4 up there, which will be better than our kinetic product, and again, better than that poor product number 3, which is just so very sad. Wait a second. Y'all lied to me. Number 3 is totally a kinetic or thermodynamic product too. It also has 3 carbons onto it. Why do I listen to you guys? I should never have done that. Look at this. Look at this here. So we see that what we should have seen is if we look at this one, it still has 3 substitutions on its alkene, right? As do 2 and 4. Number 1 has just 2 substitutions there, right? So don't kind of forget this. We're going to see, in fact, I don't know why I followed you guys. Sorry, I've learned my lesson. If we kind of number these, if I just number them that way, we're going to see something special here. These 2 products are, in fact, what are they? Something special about those 2? How might we relate these to each other?
The resonance?
Resonance? Not quite. Perhaps
I was going to say isomers, but
they
they're
are
not specific.
not quite isomers of each other. Here, let me help you out.
Are they the same?
They're the same, indeed. They are the same. So, I mean, just the way I've just arbitrarily numbered them. If I do that, we see that these are the same. We have a bromine next to a methyl that has got a double bond within the cyclohexene. There. They're in fact the same. I was thinking, like, product 3 shouldn't be that far behind. I remember one of them should be bigger than the other. So, cool. Let's relook at our product distribution here. So, still our kinetic product, which is number 1, is going to be bigger than the other ones, right? That one should definitely outweigh our other products. I'm just going to get down here so we can see. If 3 and 4 are the same, we might expect that kinetic conditions that we're going to end up with an equal ratio of 2 to 3 to 4. And that's reasonable. Just you're going to get your kinetic product first, and then the others are going to come kind of in equal proportions afterwards. But since 3 is equal to 4, they are the same molecule. We can just say 3 is going to represent the entire molecule. Because we have twice as many chances to get product 3, because remember, 3 and 4 are identical to each other, we're going to end up making more of it than product 2. So even though it's kinetically controlled, we're still going to get our kinetic product first, but then we have twice as many chances to make product 3 as we do product 2. So we're going to end up with twice as much, probably, thereabouts. At high temperatures, though, we're going to end up with number 3, because that is twice as much. 3 and 4 are the same thermodynamic product. Followed by product 2, which was also... Sorry, let me go back now here. Product 2 is a thermodynamic product because it gives us our triply substituted double bond. But product 1 here is only a doubly substituted double bond. So number 2 will still beat out number 1. But because number 3 has, again, twice as many chances of forming, because it's identical to product 4, we're going to end up with that here. So do we see kind of why this distribution is written this way? Because those two are identical. If they weren't identical, we would say maybe 1 is better than 3, which is about the same as 4, which is about the same as 2. But since they are identical, we can just kind of lump 3 and 4 together and therefore end up with actual distributions. I'm going to put our hydrogens back on just so we have them there. But remember, both of those have hydrogens, they just have them in different places. And there's nothing special about those hydrogens. A hydrogen on the other side of the alkene is still a hydrogen, right? So that is why I chose this molecule. So,
Professor,
Yes, sir.
really quick.
Go ahead.
What do we put them in order as?
Like, what do you mean? Like this order here, like 1 through 4? Like,
No, the bottom one. We,
Okay.
for example, we put low temperature and high temperature. Is it as thermodynamic products? Is that what we put them in order
So
as?
this is kind of your product distribution. So remember, at low temperatures, you're going to make your kinetic product. At high temperatures, you're going to make your thermodynamic product.
Oh, okay. I got it. Thank you.
So at low temperatures, you're going to see your kinetic product will always be favored over your thermodynamic product. And then at high temperatures, you're looking at thermodynamic products. So at low temperatures, which one is the best kinetic product? At high temperatures, which one is the best thermodynamic product? And so, again, that means comes from the most stable intermediate. For carbocations, we're looking at tertiary over the other two. Tertiary is going to be your best stable carbocation. Oops. Dynamic. That's going to be your most stable product, which is in general going to be your more substituted alkene. And so we see 3 products here have equally substituted alkenes versus that first one, which had the less substituted. But since 3 or 4 are identical, we're going to see more of those overall. All right, let me go back to horizontal mode here. I'll leave it right here for now. Do we have other questions on the kind of this distribution idea? So, big picture ideas here. Again, for addition reactions like these, where you have different kind of places of attack, a kinetic product is one that comes from your more stable intermediate. So you're looking at your carbocations or whatever, if you have radicals or whatever, you're looking at those instead, but these are carbocation reactions. So we're looking at whichever one gives us the more stable intermediate. So tertiary carbocation versus a secondary one versus a primary one. At high temperatures, because reactions go in reverse, we're more likely to end up with a larger proportion of our thermodynamic product. And the thermodynamic product is the one that is the most stable product. And for these alkene type of reactions, that's going to be the one that forms the more substituted alkene. Alright? Fun. Alright, just for funsies right now, if y'all could, just type your
Very
name.
quickly,
Go ahead,
Victor,
Matt.
I'm sorry. So for thermodynamic, would it be the opposite of kinetic? Would the primary be the most stable?
Nope. So we don't care about stability of our carbocations. We're looking at
Okay.
the substitution of the alkenes. So
Okay.
if it's a primary one that ends up giving you your thermodynamic product, that's okay. It could be a secondary one. It could be a tertiary one. Sometimes your thermodynamic product and your kinetic product are the same. So they're not necessarily the opposite of each other. So it just depends on which one's the more stable intermediate, which one's the more stable product. They could be the same, they could be the opposite. It just depends.
Got it. Thank you.
Alright. In Discord right now, could you all just real quick write your name? I have to do the attendance for the last time. So just like write your name right now. Like Elena's doing it now. Just write it, perfect, just like that. Just do that real quick while your brain kind of can reset. Perfect. You can do your whole last name, doesn't matter. Cool, perfect. Awesome. Cool. Just again, I had to submit my roster today, so cool. Alrighty. So, let's breathe for like 30 seconds before we go into our next topic here. So,
I have a question.
yeah.
So could you give a list of all like the ideas we have to kind of revisit from past chemistry courses?
Oh man.
Or is it just everything?
Yeah, right. It's so hard to say because, for example, we're revisiting our, Gibbs free energy right now, but we're probably not going to see that again for the rest of the semester. We're going to talk about molecular orbitals in this chapter and nowhere else. But dipoles we're going to talk a lot more about in carbonyl chemistry. So it's like, unfortunately, it is pretty much everything, I want to say, unfortunately. But if you had limited time, which you do, and if you were to if I were to pick some major topics to talk about, I would say they would be things from chapters 6 through 9 from last semester. Those would be the most important things for future organic chemistry. Yes, we still have stuff from 101, we still have stuff from 102, but those are more kind of here and there. Stuff from 6 through 9 about elimination, substitution, alkene reactions, those are going to be actually, I wouldn't even say alkyne reactions are less important here. So alkene reactions, yes. Substitution, elimination, yes. Alcohol reactions, yes. Those are going to be kind of the big three things from last semester. Okay. Alkynes, not so much. We don't really deal with those much more anymore. I mean, we'll have them, but they're essentially going to do the same things as alkenes would. So, yeah. So, if nothing else, I would focus on those. That would be kind of your biggest things to focus on.
Okay, thank you.
Yep. I hope those are the right chapters, by the way. I think they are. I actually have not looked at the Wade textbook in a long time, but I think those are the chapters. So, continuing on then. Review these. Okay. Alright. Let's talk about a class of reactions called pericyclic reactions. And we're going to have a couple of examples here. I'm going to just draw some arrows. We're going to see different types of reactions here. We're going to see here we will lose 2 pi bonds, and we're going to make 2 sigma bonds here. This class of reactions is called Cyclo Additions, which we're going to study first. So these are reactions that will end up causing us to lose 2 pi bonds, but in the process we gain 2 sigma bonds. We're going to have also another class called Electrocyclic Reactions. Kind of same idea here. Here we will kind of lose 1 pi bond. So we had 3 pi bonds in the first molecule, we have 2 in the other one. So we lose 1 pi bond. We gain 1 sigma bond. These are called electrocyclic reactions, which we'll talk about second. We'll go in the order here. And the last one we have are what are called, they're a rearrangement type of reaction, but let's see. We're going to see we all just rearrange these things. And we end up with essentially the same molecule, but just now. Ooh, that's ugly. We don't gain or lose anything in terms of pi bonds or sigma bonds here. So we're just rearranging things. This is called a sigmatropic rearrangement. There we go. So, 3 types of reactions. These all fall under the category of what are called pericyclic reactions. And we're going to focus in this order: Cycloadditions first, then electrocyclic reactions, and then sigmatropic rearrangements. And we're going to have kind of, at least of the last one, we're going to have a couple of name reactions there. The Cope rearrangement, Claisen rearrangement. Fun stuff to talk about there. But first we're going to do cycloadditions. So cycloadditions, again, you'll have 2 pi bonds lost in the process of a cycloaddition, and you will have gained 2 sigma bonds. If we take a look at something like this, again, I'm going to redraw the same thing. If we go ahead and push some arrows, just kind of moving things around here, we're going to see we end up with a transition structure that is kind of our 6-membered ring. So I just get rid of all of our double bonds here. Our transition our transition state is essentially a 6-membered ring. We would call this a 4+2 Cyclo Addition. We are adding a 4-membered pi system, so a diene there, and we're adding it to a single pi system, which has 2 carbons. So we're going from 4 carbons, or 4 pi electrons, and we're adding it to 2 carbons, or 2 pi electrons. And so we will call this a 4+2 cycloaddition reaction. This is also called the Diels-Alder reaction, after the scientists who did it. And we're going to kind of spend a bit of time on this because it's a very important reaction in terms of kind of industrial use, because we're making new carbon-carbon single bonds. That's something that's not very easy to do, because carbon-carbon bonds are pretty stable, so it's pretty tough to make new carbon-carbon bonds. And this is one way to do it. So we're taking 4 carbon piece, 2 carbon piece, sticking them together. Now we have a 6-membered ring at the end. And as we know, 6-membered rings are nicely stable as it is. So, one thing to note though, if you take your reactants, put them together, you can get your product, your 6-membered ring with the double bond. With some heat, you can get this to happen. However, if you put more heat, you'll end up breaking it back apart. This is called a Diels-Alder. And this is called a retro Diels-Alder. And so it can go back if we give it more heat. So we need some heat. Sometimes that's a significant temperature. In this case, with these two reactants, we're probably looking at, 150 degrees or so Celsius. So pretty high temperature. We're going to see some Diels-Alder will happen at sub-zero temperatures. So there's some energy requirement, heat-wise, to make these reactions. But there's more heat that if you want to break it and reverse your reaction, you can throw more heat at it. The reason, again, if we really want to go into it, is the entropy idea. Our best friend again. I don't want to go crazy on this, but suffice it to say, the reason that you'll go back with more heat is because of this guy. We're going to end up favoring going backwards with more heat. Just like before, this is an exothermic reaction, so same idea. The more heat you give it, the more likely you are to do a retro Diels-Alder. And that's going to be important when we talk about cyclopentadiene. But for right now, I'm going to just erase it. It's the same idea from before. Same idea. These are exothermic reactions, but we're going to end up seeing that if you put more heat on them, you can get them to reverse. So synthetically, it can be useful to do either one, but generally the forward Diels-Alder is more useful because you're making carbon-carbon bonds. All right, let's talk about some terminology here. This guy is your diene. 2 alkenes, diene, right? This one was often referred to as the incorrectly spelled dienophile. So, phile, Greek, loves, it's attracted to dienes. That's just 2 carbons, it's ethylene, right? So those two are going to be kind of working together to make this happen. We're going to see very often the diene has electron donating groups on it. Not always, you don't have to, but very often. Oh my gosh, donating, there we go, groups. Do we remember what electron donating groups are? Some examples of them. things like these. Alcohols, amines, ethers, these are electron donating groups. They push electrons into your system. And often your dienophile has electron withdrawing groups, like a carbonyl or a nitro. Those are very common with these sorts of reactions. Sulfonyl. So, common electron withdrawing groups there. We're going to see how to kind of make this reaction work, but it's pretty simple. You have to have a diene and a dienophile. You can stick all sorts of fun goodies on them, and you'll get this reaction to work. For example, if we say, aha, I've got something like this, no problem. We'll make these. The reaction works the same way. We're going to end up making our six-membered ring. And we're going to have our, you can say these are both going to be on wedges. Those are really ugly wedges, but we're going to end up with our product here. With the enantiomer, of course. But same idea happens. So the chemistry that's taking place is between the diene and the dienophile. And we're going to end up making kind of the same thing that we had before. So notice that we have a kind of cis relationship with our what are we calling these, aldehydes? There we go. And so we end up with a cis relationship in our product. Very exciting. Main chemistry though that we're seeing here is we're going to have the cyclo addition take place. So we're going to take our dienophile, make our six-membered ring with the double bond, and we're going to end up completing our reaction. Not too bad. You can do it with alkynes as well. No reason not to. Your dienophile can be an alkyne. Let's say now we have this guy. Have this happen too. Same thing. Arrows are moving the same way. We're going to make our six-membered ring. Though in this case, we are going to have a double bond still left over because we've only taken one of those pi bonds out. So we still have the other pi bond from our alkyne. And so we're going to, in this case, have our still our carboxylic acids are going to be there. So, nothing too crazy, yes? Let's do another one. Oh, I have another electron withdrawing group for you guys. I forgot nitriles. So that's another one that's pretty common. So another electron withdrawing group would be your nitriles. So let's say we've got this trans now. Doesn't matter. Your dienophile can do whatever the heck it wants. We're going to see with the diene that's not the case. But with the dienophile, do whatever you want. We're going to end up, because these guys are trans to each other, same idea. They're going to be trans to each other in the product as well. And you'll still have your enantiomer. But that's the case here. So we're going to end up, if you had a trans alkene as your dienophile, you will end up with a trans relationship between your substituents in your product. If you had a cis alkene, you're going to dienophile, you're going to end up with a cis relationship in your product. So, same things happen. If you have an alkyne as your dienophile, you're going to end up with a double bond, and so there's not really a cis-trans relationship because there's still no chirality here. So, cool. Any questions on these three? They're pretty nice, happy reactions, right? Let's see. Let's give you some more examples, perhaps. What are we going to get out if we put this one? If we do this, what do we get? Same old thing, right? Nothing too crazy here. If we draw the arrows, we see we'll end up with, as always, our favorite six-membered ring. And everything else is still cyclic on it. So, oh, that's real ugly. But nothing changes with the rest of the molecules. So, we're kind of nice and happy here. But this is too easy, isn't it? You guys aren't going to be crying in the shower if this is all that is taking place, right? This is not nearly frightening enough to be organic chemistry. So, let's kick it up a notch. Let's say now we have something on our diene. Let's say now we have these two guys. All these previous ones I've given you have been symmetrical. And so we end up with one product. Plus or minus an enantiomer or whatever, that's okay. Essentially one product. Right, all these, one product. With an asymmetrical, when both are asymmetrical, we need to look at partial charges. And how the heck are we going to get partial charges here? Well, the answer, let's go ahead and do some resonating. And let's see where partial charges might be located on these molecules. So if we just take a look at the diene, the one with the nitrogen on it, if we resonate things, notice this is an electron donating group. Donating groups push electrons into something. If we resonate this, oops, why did I circle the double bond? Oh. So, if we have this, we see that through resonance, if we felt like it, we could push electrons onto carbon number 4 there, down at the bottom, giving it a negative charge. If we really wanted, we could also have said, okay, well, let's mess with this some more. Let's push those back, and this time let's go ahead and stop right here. We could do that either way. So now we've got our lone pair and negative charge on carbon number 2. And these are kind of the three, these are the three resonance forms that we have. We have the no charges, plain old. We could see with resonance, we could end up with negative charges on carbons 2 or 4. So, we're going to see that carbons 2 and 4 are going to be slightly negative as a result. If we just want to think about them, if we want to think about how resonance can help us determine which carbons can hold a little bit more electron density, we're looking at carbons 2 and 4 here. Is that okay? Do we see how that resonance is pushing electron density onto carbons 2 or 4 from the nitrogen? It is donating electron density to those two carbons. Hopefully not too bad. If we look at the other one, if we look at the dienophile, if we resonate this, it'll be a little easier because we only have one thing we can do. We end up with a positive down on carbon 2. And so we'll say, aha, well, this one, therefore, by resonance, is just going to be a little bit positive. That carbonyl there is withdrawing electron density from carbon 2, or I guess carbon 3, because the carbonyl has a carbon on it. But that one down there. Because we see with resonance, we end up with a positive charge there if we were to resonate it in this way. Not really much else we can do in terms of resonance. And so, we're going to see that the most likely way that this is going to react is going to be connecting these two carbons together. So it's really the same way we've done it before. In this case. We'll see if we do other things, something else might happen. And so as a result, that's where we're going to be pushing our electron density. So electrons are going to be pushed down. Carbon 4 being slightly more negative is going to be attracted to carbon 3 in the dienophile. And so we're going to see that that's where our reaction is going to be taking place. So we're going to see, I'm going to go ahead and redraw these down below a little bit. If we just kind of push everything, all of these resonances, we're going to see that this is going to attack the negative carbon 4 is going to attack positive carbon 3, and therefore this one is going to come back and form the last bit there. And so as a result, we end up with the same kind of thing we've done before. We're going to have our 6-membered ring. In this case, we're going to have positive nitrogen because that's where I decided to start this. And we're going to have our oxygen up here. But as a result, because if you see here, we're putting too many things onto this, we really have to kind of do this in 2 steps for the resonance to make sense. So let me do it that way. If we do it fully resonance style, so then this is going to end up being our negative bit here. And we're going to say, aha, well, this is just going to come down. This part's going to form the double bond. We're going to kick those back up. And so if you want to think about it in terms of resonance, this is what it's going to look like. So kind of just pushing electrons all the way through, we'll end up with our product, which will be the six-membered ring with the amine and the carbonyl kind of right next to each other. So again, this is kind of like a not quite there, because we do see that this is going to be a concerted process. We might consider this part of our transition state or something. So just to help us out with the resonance, to see how we're going to form these two next to each other. We're going to see sometimes it'll be the opposite case. If we take a look at the same dienophile, but switch the diene, I see, by the way, Ani there has shown up at 1025. Very good. If we have now instead our nitrogen over here, and our same dienophile, well, this time we're going to see that resonance would actually push electron density to carbon 1 here. So it's going to be pushing the electron density towards that carbon. And so as a result, this time we're looking at our negative carbon being the top carbon, and our other one is still the same, the bottom carbon being the positive one. So it may be better to redraw our electrophile upside down so that our positive and negative are kind of close by. And then we can see what's going to happen here. We can see, aha, well then we're going to form our six-membered ring as before. If you really wanted to do the kind of transition state with the resonance, you could. It'll be much the same as this, except we'll have things moved slightly. So the big thing, though, is that we form that bond between the positive and negative there. So from those two, we have to make sure we connect those two carbons together. And so as a result, we end up, again, six-membered ring, just like before. We're going to end up this time with a kind of 1-4 relationship between our substituents. So previously, we had a 1-2 because our diene had electron density on carbon 4. Poor Oz is like dying down there. He's got tracheal collapse. I don't know if you guys can hear that. He's like constantly wheezing. I don't know if it's distracting to you. It is to me. But anyways, if we have our electron donating substituent on carbon 2, it ends up pushing density into carbon 1. That carbon, therefore, is going to be the one that attacks the positive part of our dienophile, thereby leading us to a different arrangement in regiochemistry. So you're kind of electron donating and kind of substituents can determine regiochemistry. So which carbon gets attacked and which carbon is doing the attacking, that's regiochemistry, right? Which area is the reaction happening. So we had the same dienophile, we just changed our diene slightly, we get two different products out. So one product we get our two kind of next to each other, carbons, or like say 1-2 relationship. In the second case, we end up with a 1-4 relationship here. So it just depends where your dienophile and diene have their substituents, and that'll give you the kind of regiochemistry. So we are out of time for today. We'll continue this exciting topic on Wednesday. Like I said, don't worry, you will cry about this reaction. That sort of bit is going to come when we start talking about using cyclopentadiene as your diene. And then you'll end up with these 3D structures. It'll be so fun. But we'll get there on Wednesday. So, for right now, you may want to take a look at some of the problems in, the back of your chapter and practice your Diels-Alder skills. So, and your 1-4 additions and all that. So, that would be a good idea. So, I think Chalmers will do more tomorrow with you guys on this, so we'll keep practicing. Alrighty, so I'll see you guys next time then. I guess I do have office hours today, since we've decided. So at, 12:15? If y'all want, you can ping me here and I'll show up and we can do questions and answers and stuff. So, cool. With that, I'll see you guys later. Enjoy the rest of your day.
Thank you.
Yep.
Have a good one.
You too. Yeah.
Real quick.
Yeah.
This is chapter 15, right?
Maybe. I don't remember the chapter for this. I think so. That does sound familiar. Let me quickly check. Wade, Organic Chemistry, 9th edition. Yes. Give me your table of contents. Should be something like called conjugated systems or something like that. But let me find
I think that's 15 then.
Okay, yeah.
Because on the syllabus it says conjugated systems.
Yeah, that's what we're looking at. But is this Pearson? I think it is. Yes. Yeah. Okay, table of contents. Yes. For sure is 15.
Okay, thank you.
Okay. Oh my gosh, then that means I got the reaction or the numbers wrong for the other chapters. Oh shit. Oh well. We'll deal with that next time. Whatever. Okay.
Thank you.
Yeah, sure. See ya. Yes, Hav.
Wow. So can I work in the lab?
No.
Why?
Well, talk to the Armenian lady. I don't want to go to lab. It's only Dog Geek's class. You really want to listen to him talk?
So long as you get paid.
Oh my god.
Wait, he's doing a class in person?
Yes. I think it's the stupidest idea. But
What class?
102 lab. It makes no sense. But yeah. Alright, I'm gonna go, dude. I have
Can I see your
freaking
dog?
Newman projections to do with the other students today. They killed. Oh, it's the worst. Alright, see you later.
Can I see your dog?
Yes, quite.